Welcome to the second lesson for Newton's laws. This lesson will be on Newton's third law of motion, but we will start by talking about gravity and something created by gravity, which is called projectile motion. You should have your Newton's third law sheet out in front of you right now. You should be ready for any of those hidden talking points throughout the whole thing. First, we're going to talk about gravity. Letter A says that anything that has a mass exerts an attractive force on everything around it. This is called gravity. So basically everything that you can see in this picture is creating gravity. The planets, the sun, even your textbooks, you have gravity about you. And that's going to lead us into letter B. And what letter B is saying, it says that the law of gravitation, so you need to write law of gravitation, says that any two masses exert an attractive force on each other. The only thing close enough to you and with enough mass for you to feel its gravity is the Earth. And that's right here. Your textbook, even though it has gravity, is too small to exert a mass on you. And even though the sun is much, much more massive than the Earth is, or than your textbook, it's too far away. Like if you look in this picture, the Earth is the sun, is much, much bigger than the Earth. This little dot here is the Earth, and this big thing here is the sun. But because the sun is so much further away than the Earth, you only feel the Earth's gravity. So it depends on a couple things, just that mass and the size. Okay. The last thing we're going to talk about is a picture of this galaxy here, and this is going to take us into letter C, really. And what letter C says, it says that gravity exists between all objects in a galaxy. And it's what gives a galaxy its structure. So you should have galaxy and structure there, and that should be by letter C, so if you don't get that. And the very last thing that we need to talk about here is letter D, and we won't need any of these letter D, so I'm just going to get them out of the way. And letter D says that gravitational acceleration describes how much force something has as it falls. Acceleration from gravity is 9.8 meters per second squared. And then the force that this applies is described by the equation where force, and you should write this below there, force equals the mass times 9.8 meters per second squared. So that's your equation to find the force due to gravity. We'll practice with that a little bit more later. Now we're going to talk about a couple things called weight and mass. Letter A says Newton's second law states that if you are standing on the floor and your acceleration is 0, the net force acting on you must also be 0. But does that mean gravity stops acting? No, the floor exerts a force upward that stops you from falling. So if we look at Aaron Rodgers here, basically gravity is pulling Aaron Rodgers down like this. So it's going to pull Aaron Rodgers down. But the floor that Rodgers is standing on is pushing back up on him just like this. So they're equal and opposite. That's why he doesn't fall right through the floor. If there wasn't a force from the floor, he would be falling right through it. Letter B then says the gravitational force exerted on an object is called the object's weight. Your weight in newtons is equal to your mass times the acceleration due to gravity. So we have a problem here for us to do. And if you need that, you can pause it here and you can still use this picture. We have a problem to do here. Problem says if Mr. Neubauer's mass is 84 kilograms, what's Mr. Neubauer's weight in newtons? So what we need to do for this problem is we have to have our force is going to equal my weight, which is 84 kilograms, or my mass, sorry, and times Earth's acceleration due to gravity, which is 9.8 meters per second squared. So my weight in newtons, if we multiply this out on a calculator, is going to be 823.2 newtons. So quite a lot, actually. Now, you can write that one down, and we are going to move on and talk a little bit about the difference between weight and mass. So this is going to take us to letter C down there, and we're going to use this other picture to help us talk about weight and mass a little bit. Letter C says that weight and mass are not the same. Weight is a force, so like we just did where we had a newtons there, and mass is the amount of matter an object contains. The greater an object's mass, the greater the force between that object and Earth. So the weight of an object also depends on the gravitational force of Earth. And you know what, I wrote that kind of poorly, so let me erase that for you guys, and I'll write out gravitational again just so you guys have it. So it depends on the gravitational force of Earth. So for an example, a person weighing 480 newtons on Earth would only weigh 80 newtons on the moon, but their mass is still the same. So if you look at this picture of these astronauts here, you can see that this guy's mass is 100 kilograms. So on Earth he weighs 980 newtons, but his mass is still 100 kilograms on the moon, but there he only weighs 162 newtons. And the reason is because the Earth is so much bigger than the moon that it has way more gravity than the moon does. So something that's bigger in size has more gravity. Now we're going to talk a little bit about something called projectile motion. A, you don't need to write anything, but A says that thrown objects do not travel in straight lines. They tend to curve downward. So just like this football over here, you can see that it doesn't really travel in a straight line, it curves downward, and that's because of gravity. Letter B then says that any object that is thrown or shot through the air is called a projectile. So the pictures on the left show you two examples of projectiles. One is the bullet, so it's flying through the air, and the other, all the food that's flying around, those are projectiles as well. The rest of that says projectiles, so you're going to write projectiles again. Projectiles follow a curved path because they have horizontal and vertical velocities. This is due to their own inertia, which means that they're basically their momentum, their motion forward, and due to Earth's gravity. To do letter C, we need to get these out of the way, so I'm just going to move this, move these pictures, and we're going to look at the picture of this football here. So this is going to help us out a little bit with letter C here. Okay, C says that when you throw a ball, you give it horizontal motion. In this case, when you kick a ball. So you can see that he's kicking this ball, that's giving it horizontal motion. It means motion moving this way. But if you keep looking at the picture, you'll see that as soon as the ball leaves your hand or foot, Earth's gravity starts to pull it down. So it travels forward and downward. So you can see in the picture, like the football is moving this way and it's moving this way. That's why it moves in this curved path like that. And then letter D says that a ball's vertical and horizontal motions are independent of each other. A ball that is thrown and a ball that is dropped will hit the ground at the exact same time. And I'm going to prove this to you later in the week when we do a couple demos. All right, the fourth part here, we're going to talk about centripetal force. And first we're going to talk a little bit about centripetal acceleration by letter A. And A says that centripetal acceleration is acceleration, so please write acceleration, and it's towards the center of a curved path. So basically, if you look at this picture over here with the roller coaster is moving around this curved path like this, and that means that it has some force that's moving towards the center of the circle. That's why you feel like you're being pushed basically into the cart when you go around a circle like that. Letter B here says that centripetal force is the force that pushes an object towards the center of a circle. And this is what keeps a car on the road as you round a sharp curve. So it basically stops your car from just flying over the end of the curve. It's because it has a force going towards the center of that curve. All right, now we have a few examples where we're going to work with that force and weight equation. So number one here says if my mass is 165 kilograms and I fall off a building, what force will I fall with? Now we got to remember that force equals our mass times our acceleration. But our acceleration is always 9.8 now because that's what Earth's gravity is. So to solve this problem, we're going to take 165 kg or kilograms and multiply it by 9.8 meters per second squared. Okay, so that's going to give us our answer here. So we're going to take 165 times 9.8, and it tells me I would fall with a force of 1,617 newtons. So that's quite a bit of force coming down. So if I crash on somebody, it's probably going to do some damage. Number two said, what is the weight in newtons of a 1,450 kilogram pickup truck? So we're going to use the same equation from above. We're going to write out 1,450 kilograms, and we're still multiplying by 9.8 because, once again, that's the acceleration due to Earth's gravity. This time, if you punch this in your calculator, you're going to get 14,210 newtons. Now we're going to talk very briefly about Newton's third law. Newton's third law is a little bit shorter than the first two. What Newton's third law says, it says that for every action there is an equal and opposite reaction. In other words, when an object exerts a force on a second object, the second exerts an equal force in the opposite direction. So if we look at our pictures here, this is how a rocket really works. So basically the rocket is exerting a force in this direction. Okay, so it's blowing out all that fire and stuff, but that fire is what basically, and all that explosion is what propels the rocket forward in this direction. Okay, in this case, the bullet needs some sort of force pushing this way to go forward. But what happens is that there has to be an equal and opposite reaction. So anybody that's ever shot a shotgun before knows that this butt of the shotgun pushes back into your shoulder, and that's what we call recoil. And the same thing's happening with the two skaters down there. So for B, for examples there, you just write two of these three examples down. So either the rocket going into outer space, two skaters pulling each other, or you need to write the recoil from a gun. Now that's by letter B. All right, in the last slide here, we're going to talk about momentum, and there's just words for this one. So letter A says that momentum of an object is equal to its mass times its velocity. It's a measure of how much force is required to stop an object. So we could figure out how much force we need to stop, a truck or a person or a ping pong ball or a golf ball or any of those things. Letter B says that fast moving objects are harder to stop than slow-moving objects. Just like objects with a lot of mass are harder to stop than objects with low mass. So all this is saying is that things that are heavy and move fast are harder to stop than things that are small and move slow. So a truck moving fast takes more energy to stop than a moped moving fast. It's just because it's bigger, which makes sense to us. Letter C says, when objects collide, momentum is conserved. When a cue ball hits a group of pool balls, the momentum the balls gain is equal to the momentum the cue ball loses. This is called the conservation of momentum. This is going to conclude Lesson 2 from Newton's Laws.